How far away would a small object need to be from Earth to feel the same force of gravity from a similar object nearby? Today, we're going to learn how to use Isaac Newton's genius to solve this type of problem. Specifically, Newton's law of universal gravitation. This law states that whenever we have two masses, m1 and m2, separated by a centroid distance r, the force of gravity acting on them is described by this relation. In Newton's formula, g is the universal gravitational constant, m stands for mass, and r is the distance between the mass centroids. Let's try a problem. Consider two iron spheres of equal mass, each with a diameter of 100 millimeters. How far away would a single sphere need to be from Earth to feel the same force it would from another sphere placed right next to it? To solve this, we need to consider the two scenarios described in the problem. In scenario 1, we have two identical objects with equivalent masses ms. Because they are spherical and right next to each other, the distance between them, rss, is equal to 2 times the sphere radius, or just one diameter. Note that each object is exerting the same force on the other, but we're only interested in one. In scenario 2, we have a similar setup. Only one of the masses is Earth, and the distance between the objects, RSE, is unknown. RSE is the distance the problem is asking us to solve for, the distance between the small object and the Earth. We want to find RSE such that the forces in each situation are the same. Since we know how to apply Newton's law now, we'll apply them and see the force described for each. With those written out, let's see what happens setting FSS equal to FSE. We can see that since there is a g and an ms term on each side, we can simplify the equation by dividing them out of each side, and we're left with an equation in terms of the two masses and distances in our problem. Since the problem is asking for the distance from the sphere and the Earth, we can rearrange the equation to find this expression for RSE. We already know RSS, and we can look up the mass of the Earth, which is about 6 times 10 to the 24 kilograms. The only remaining unknown is the mass of the iron spherical object, which we can determine by calculating its volume and looking up its density. The expression for mass is m is equal to rho v. The density of iron is 7,870 kilograms per cubic meter, and the volume of a sphere is pi divided by 6 times the diameter cubed. We can now rewrite our mass equation in terms of density and diameter. With each variable accounted for, we can substitute in values and find the mass of the sphere, about 4.1 kilograms. Let's recap what we have for our final equation and solve the problem. The distance between spheres is 0.1 meters. The Earth mass is 6 times 10 to the 24 kilograms. And the small mass is this value. Substituting in values and calculating, we can see that the distance is about 1.2 times 10 to the 11 meters, or about 120 million kilometers. Wow! To put that into perspective, our distance of 120 million kilometers is about 80% of the distance between the centroids of the Earth and the Sun. Today, you've learned how to use one of Newton's great discoveries to study the effect of gravity in our universe. Thanks for learning. Subscribe for more physics and engineering lessons.